So it is a tutorial for hardware design, very basic stuff, but it can give you guidelines about things you can do. So it's for things like that, it's not for software. And more particularly, okay. And more particularly, it's for designing no mouse. This kind of circuit of chip. And there are two kinds of chips. There are some that are analog, so they handle various signals, and some that are digital. And so it's a talk about digital design, digital chip. Okay, the first thing to know is that designing a chip is very complex, requires a lot of knowledge, a lot of tools, and it's also very, very, very expensive. Well, only big company can afford to design a very complex and a very big chip. Hopefully, there are some kind of chips, like this one, that can be programmable by user. So the features of the chips are completely defined by the user. Usually it's defined by the builder of the board, but you can buy board with this kind of chips and program it by yourself. It's because it has a very particular architecture, which is composed of a logical block, so where you can define the logical function that will be done, and a network of connection that is also programmable, and the user will also define how the signals are routed within this network. And there are also pads, so what are available on the connectors, and they are also programmable, at least to set direction of the pad and other features. Well, it's a talk about digital circuit, so we are only speaking about 0 and 1. It's very simple. It's about binary logic. So the way to do computation on binary logic is using gates. There are, I would say, 3 basic gates, which is NOT gate, so it just inverts the signal. If you add a 0 at the input, you get a 1. If you add a 1, you get a 0. It corresponds to the TID in the C language. You have OR gate, so as soon as one of the input is 1, the output is 1. If both inputs are 0, the output is 0. This corresponds to the logical pipe operator in C. And there is the AND gate, whose output is 1, only if and only if both the inputs are set to 1. And this corresponds to the ampersand operator, to the AND operator of C. Well, this looks like very simple, maybe too simple. You can say, okay, what can we do with only 3 operators, 3 logical operators? But you get a lot of power by combining them. So for example, usually the XOR, so or exclusive OR operator, which is expressed with a caret in C, can be created by all the previous gates. So here, if both let's ignore. If both output are 1 and not both input are 0, the output is 1. This is the usual symbol for XOR. And with the XOR gate, you can also do computation, well, mathematical computation, like for starting an adder. So an adder, 1-bit adder, is in fact a XOR gate. So an adder is a little bit simple, and we can complete it by designing what we call a full adder. So I would say half adder is a simple adder and the carry. So the carry is 1 only if both inputs are 1. And if you want to be a little bit more complete, you can design a full adder with an input carry and output carry. So it becomes a little bit complex. It handles all the various cases of the possible inputs, value of the inputs, and generates the sum and the output carry. And usually it's too complex to be written like this, so on scheme you abstract with a box saying, okay, it's an adder. And with this full adder, you can do things a little bit more complex because you can group them together. And here you have a 4-bit adder. And if you want to 32-bit adder, you can just replicate this scheme several times. So you have inputs A and input B, the sum, and at the end, a carry that you can ignore. This is how you do a summation, an addition in hardware. And if you can add watts, you can also multiply. So you replicate the adder several times, and you either, it's like a multiplication on the paper and pencil. You add only if the bit is set to 1, and each time you shift. So this is how you can do a multiplier in hardware, starting from adder, starting from simple gates. So, as you have seen, just using simple logical gate, you can do, I would say, almost any mathematical function, well, almost any simple mathematical function in hardware. So from you have inputs and you compute outputs. That's nice, but in fact that's not that powerful because very quickly your design becomes very, very big. You have seen how big is a multiplier. If you do lots of multiplication in your computation, it will be very, very large. And one way to shorten the computation is to use recursion. You want to reuse the output as inputs. Unfortunately, or as a matter of fact, you can't do that easily. The reason is because hardware is not about only logical concept, it's also about physical concept like time propagation. If you come back to the full adder, there are 3 inputs, and in fact the times, each time there is a gate, it takes time to compute the output because there are some capacity in the design that are hidden. It's not lightning fast. It takes time to compute the output, and as a consequence, the outputs are not ready at the same time. So you may expect a perfect output, like in this diagram, but in fact, for example, the output of A0 comes just before the output of A1. And if there's a loop, it will drift more and more. And for example, the output of A2 will be available much later. And because of that, you will have wrong outputs at many times. So you don't know where is the correct output. So you can try to avoid this nasty effect by, for example, balancing the circuit, but it's very, very, very hard. So the main rule when you do digital design is never have direct feedback. And the way to solve that is to use what we call a register, a memorizing element, which need a clock. And this particular gate, what we call it a flip-flop, will memorize the input and will reflect the input only at some times when the clock is active. So here, for example, the clock is active, so the input of the flip-flop here will be reflected to the output just when the clock is active here. Again, here the clock is active, the input is here and will be reflected on the output here. And with this kind of circuit, you have a perfectly clean output. That's the reason why we always use, almost always use clocks in digital circuit, and that's the reason why any digital circuit has a maximum clock rate due to the time it takes for the loop, and there's also performance attached to any digital circuit. So most of the digital circuits are composed of logic gates that do computation and flip-flops or registers that are used to synchronize the circuit, the computation. So that's the base of how to design a circuit. Computation, synchronization. It's possible to design a real circuit using schematic editor. Well, it works well for very simple circuit, but as soon as it becomes a little bit complex, people prefer to use an HDL, which is hardware description language. It's like a language, a C language or Java language, but that target specifically hardware. There are two main hardware language, Verilog and VHDL, and here I will use VHDL. So we have this kind of board with a programmable circuit, FPGA, and since about 2 years we have a complete open source software tools to program this kind of circuit. So there is a synthesizer named Yosys. There is a place and route, I will explain that later, that is named directly place and route. And there is iStorm, which is used to create the binary stream to program this circuit. So this board is about 20 euros, so very affordable, and it is supported by open source tools. So it's very nice for beginners. So the first, only example using VHDL. This describes an entity describes the interface of the circuit, which means how it will communicate with the environment. So there is one input, which is the clock, and on this board, the clock is generated by a circuit on the board, and 5 outputs, which are routed on this circuit on the 5 LEDs. Well, it's not very easy to see it, but I will show. So you just describe with an entity the interface, inputs and outputs. And in VHDL, you have the architectures which describe the internal of the circuit. So I have an intermediate wire which is internal clock, because the external clock is 3 MHz, and if I try to blink the LED at 3 MHz, you will see nothing. So I use a divider to divide to 4 Hz, which is visible at this point. So all the LEDs will be blinked together at 4 Hz. And how I convert from 3 MHz to 4 Hz, I just use a counter that is incremented each time the clock has a rising edge from 0 to 1. So each time the clock is rising, either I have reached the top of my counter, which is 3 million minus 1, and so I reset the counter to 0, and then I switch the clock. Or if I haven't reached the maximum of my counter, I just increment it. So the counter will increment it until 300, and then at 300 it will revert to 0 and switch the 4 MHz clock. You have to know that in any hardware description language, everything is parallel. So this executes at the same time as this one, this one, this one, this one, and the process executes at the same time as this one. Everything is parallel, except that within the process, execution is sequential. So this is not a tutorial, a complete tutorial about VHDL. It's just a view of how it's done. So once you have written the entity and the architectures, we will go to synthesis, which means we'll convert it to binary code used to program the FPGA, and using the GHDL frontend, you first analyze the files, so you let the compiler know about these files, and then using the synthesizers, you say, okay, I want to generate a circuit for LEDs, which is known here, and I want to target this FPGA. So this FPGA is ICE 40. And you specify the output file. So there is a lot of processing that is done on the input file. And it generates what we call a netlist, which is a net of gates and of registers. And then you can use hierarchy PNR to place all these gates. So it will try to assign each gate to the logical blocks of the FPGA and to route all the nets. But it's a little bit technical. It's done completely automatically. And if it works, you're okay. And with it, well, usually it works. It doesn't work if, for example, you are using too many gates and there are not enough gates on the FPGA, or if you are just at the limit, the place and router can say, no, I cannot find the routes. And when you place and route, you also specify which paths is assigned to all the inputs. And then you have to program the FPGA. So in fact, on this board, you have a USB connector, and the USB connector is connected to a flash. So you write a binary to the flash, and the FPGA, when it is started, it will read the binary from the flash and program all the root network and the logical block. And once you have flashed, you have written your binary stream in the flash, it's okay. So it's not exactly the one I have programmed. But you could see LED blinkings. Well, in fact, it's rotating. It's a slightly more elaborately designed. It's rotating, but almost the same. So this is all the open source tools I have used. Okay, I am the developer of GHDL, so that's why I've used it. Yosis is a synthesizer, but it also Verilog front-end, which is more well, it is almost featureful, while the VHDL front-end is just well, it's still work in progress. But that's so you have a really toolchain, open source toolchain for this kind of FPGA. And that's it.
We have time for a couple of quick questions. Which manufacturer is the FPGA coming from?
It's latest semiconductor. Well, if you look on Google for ICA40, you will find it.
Can I debug the program?
Debugging. Good question. Well, there are many answers. First, if you don't debug, you don't need to debug. Second, what you can do with once you have written your design, you can simulate it. So it's completely software approach, and you can see, you can try to feed inputs, and you can see what are the outputs. Or you can write test bench to be sure that your design behaves correctly. And sometimes it behaves correctly on the paper, I would say, and when you program, it doesn't work. And then it's not easy. Usually you have to add some circuit to try to understand what happens, and using the oscilloscope. But on that, this card is difficult.
But then is it possible to add digital proofs for the live debugging, or not really?
Yes, but only on the external pads.
On the external person,
Yeah.
no internal digital proofs?
No, unless you want to add your own circuit that try to read various nets and outputs on the external pads, but no.
Okay, maybe I missed. Is it open source tool for simulations?
Yeah.
GHDL?
GHDL does simulation for VHDL, and Icarus Verilog does simulation for Verilog. So it's complete.
Thank Tristan again.